Hey guys, so you guys are just gonna have to follow along my PowerPoint because I couldn't figure it out how to record myself and present. So you guys are just gonna have to follow along. But anyway, in today's lesson, I'm gonna be talking about flat panel detectors in digital radiography. So, what is digital radiography? It is a form of X ray imaging where digital sensors that are found in FPDs or flat panel detectors are used to immediately produce a digital image instead of using traditional film or PSP imaging plates that are found in CR or computed radiography, which is also a type of digital radiography, but today I'm going to be focused on flat panel detectors. So using flat panel detectors in DR allows for faster processing and higher quality imaging. And those images that are produced can be viewed, stored, and shared with other healthcare providers more easily and quickly by using a system like PACS. So what are flat panel detectors? So they are the most common detector used in digital radiography, where X-rays are converted into electrical charges either directly or indirectly, and then that electrical charge is read out using a thin film transitor or a TFT array. So in the PowerPoint, I just kind of have a quick summary of both of those types of FPDs, which is direct and indirect. So indirect, there is no light step. It just goes directly from X-ray to electrical signal to the image. Whereas indirect, there is a light step, and it goes X-ray to light to electrical signal to the image. And then in the bottom, I just kind of have like a quick acronym that helps me, which is XE for direct, which is X-ray to electrical signal. And then indirect, I have XLE. The L represents kind of the light step. So for direct, the first one I'm going to be talking about is direct flat panel detector conversion, which is where the X-rays are converted directly into electrical signals, skipping the light step completely, using a photoconductor layer made out of amorphous selenium. So the steps for direct conversion are super simple. It goes from the incoming X-ray hits the AC photoconductor. That photoconductor releases the electrons to be read out by the TFT array. And the TFT readout goes directly to the ADC to produce the image, or the analog to digital converter. So the X-ray just hits the photoconductor straight away. And in the next slide, if you scroll, you'll be able to see a picture that kind of, I think, summarizes it, because I'm a visual learner, so I feel like the picture really shows better. So how I remember it, which is selenium, the conductor, will take you straight to the image. So kind of selenium to represent that it's the photoconductor, and then straight to the image, meaning there is no extra step. It just goes from photoconductor to electrical signal to the image. And then in the next slide is where I have the picture, which just kind of shows the X-rays, which are the red squigglies, hitting the photoconductor, which that turns into the electrical signal that hits the TFT and goes directly to the ADC. Next, I have the indirect flat panel detector conversion, which is a little bit more complicated and has a couple more steps, or one more step. So indirect flat panel detector conversion is when the incoming X-rays are converted to light via a scintillator, and that light is converted into an electrical signal. So basically they have a scintillation layer that the direct conversion didn't have. So there's two types, CCD and a TFT reader that uses a photodiode. But first I'm going to talk about the scintillation layer, because both the CCD and the TFT have that, which converts the X-rays photons into light. So the two types of scintillation layers are gadolinium oxysulfide, which are made from small crystals bound together in an unstructured or turbid granules. It's more rugged and durable because of that, and it's less expensive. But because it's unstructured, it has little air pockets that allow for more light spread, which decreases spatial resolution. So it's not really preferred. If it is used, it's mostly used in portables because it is more durable and you can kind of play with it more, I guess. Whereas next we have cesium iodine, which is made from growing very thin crystalline needles, making it a structured scintillator. And because of its needle-like columns, is able to focus the light photons more, and because of that, there is less light spread, which means there is a higher spatial resolution because there is that less light spread. So how I think of it, I just think of cesium iodine as little eyes going down that kind of point straight down. That kind of helps me remember that it's more structured and more like needle-like, the little eyes. I just connect the eye and iodine. So like I said, there's two types of indirect conversions. First, I'm going to talk about CCD in that next slide, which just shows a picture of kind of the CCD and how that conversion happens. So the first step is the X-ray photons hit the scintillation layer. The scintillation layer then converts the X-ray photons into light photons, which those are directed to the CCD using lenses or fiber optics. And those CCD sensor chips are the ones that convert the light photons into the electrical signal. The CCD sensor chips then send that electrical signal to the ADC, and then the ADC sends information to the computer producing the image. Next, I have the indirect photodiode conversion. So the photodiode is what converts the light that is received from the scintillation layer into an electrical signal. So the photodiode is made out of amorphous silicone, and how that works is, as you can see in the picture, the X-rays are going to hit the scintillation layer, which is mostly made out of cesium iodine. That scintillation layer is going to convert the photons into light, and those light photons are going to hit the photodiode layer made out of amorphous silicone, which converts the light into electrical signal. That electrical signal is then going to hit the TFT array, and that TFT array is going to send the electrical signal to the analog to digital converter, or the ADC, which the ADC is then going to send that information to the computer to produce the image. So the pros and cons. So the pros of direct flat panel detectors are they produce more higher quality spatial resolution images. There's less blur, and there's more. It provides more detailed imaging, which is why it's preferred in mammography, because you're able to really see all those tiny calcifications that you wouldn't be able to see with indirect flat panel detectors. The cons are it's more expensive because of that, and it is more sensitive to heat and damage, so you can easily damage it. And the other con is it's mostly only used in mammography, so you won't really ever find that in general radiography departments. Basically, I think it's exclusively seen in mammo. Whereas indirect flat panel detectors are more affordable and can be used in various ways in the radiography department. For example, it can be used in the regular kind of wall or table Bucky, and it can be used in portable machines, and I think it's also used in fluoroscopy and angiography procedures. So it can be used in a variety of ways. And if you're using cesium iodine as the scintillation layer, you can get better, higher quality images, whereas if using gadolinium oxysulfide. And it costs less than direct flat panel, which is why it's one of the ones that's mostly used in general radiography. And because it's kind of cheaper, it's easier to replace if it does get broken. The cons are because of that light step, it causes some type of loss in spatial resolution because there is that light step. Even if you are using cesium iodine, it's still going to cause some type of noise and blur and potential loss for detail because of that light step. Whereas in direct, you're just going directly from kind of the X-ray photons to the electrical. So you're kind of adding that extra step in indirect, which that extra step causes some type of loss of detail or loss of information, which causes potential for noise and other various things. So that's basically it. Overall, if you're going to be working in the general radiography department, you're probably going to be using indirect flat panel detectors because those are mainly used, whereas in mammography, you're going to be using direct flat panel.